Hello and welcome, class, where we are continuing our march through Chapter 5. In our previous lecture, we talked about what it meant to be an ionic compound. Now we are going to talk about what it means to be a molecular compound. So as a reminder, ionic compounds were a combination of a metal cation and a non-metal anion, where there was some complete charge that was being caused by a total transfer of an electron from one species to another. Specifically, the metal transferred an electron to the non-metal. When it comes to molecular compounds, this is not the case. We are not going to see a complete electron transfer. Instead, we are going to have to form stable bonds, form complete octets in another way. So let's talk about that. Okay, so a good way to get kind of a visual for what happens when molecules form is by writing out what are known as Lewis dot symbols. A Lewis dot symbol, first written by Gilbert Lewis, who was working with trying to reconcile like our understanding of what it meant to be a molecular compound versus an ionic compound. He wrote out these symbols that were meant to represent the valence electron configuration for a main-bodied element. So if, for instance, we observe something like lithium with a valence, or with a total electron configuration of helium with a 2s1 electron, the Lewis dot symbol illustration for this instead illustrates lithium with a single dot next to it. This single dot is meant to represent that one valence electron that lithium has. Carbon, as another example, has an electron configuration with a core of helium, 2s2, 2p2, and this element then translates into having a Lewis dot symbol with a carbon in the center and 4 dots all around it, where each of those 4 dots represents one of these 4 valence electrons. And we can illustrate similar symbols for any main-bodied element, so long as it has valence s and p electrons, so long as it's in the s or p block, we can write out a pretty straightforward notation for the valence electron count. What this does for us is it gives us an idea for like what electrons either can be straightforwardly lost, like in lithium's case. There's only one electron here, so it's going to be very easy to lose that one electron and create a lithium with a plus charge. Or in elements like carbon, where we could lose 4 electrons or we could gain 4 electrons. We're kind of in this in-between, right? Like, what's going to end up being more stable? Well, it turns out for elements like carbon, the most stable approach is to not lose or gain anything at all, but rather to share electrons with other atoms around it. Lewis's theory of bonding stated that unpaired electrons in elements such as carbon would be shared between non-metals to satisfy their octets, or, in the case of hydrogen, the duet. So if we write out the Lewis dot symbols for elements like oxygen, carbon, and hydrogen and arrange them in this kind of nice straightforward way, Lewis's approach was to observe these unpaired electrons, these single electrons present inside of the Lewis symbol, and connect them. Right, we're just connecting the dots like how we used to do in our like coloring books when we were in kindergarten, first grade, wherever you were in elementary school. Who knows, maybe you still do them as a means to relieve stress, like I don't judge. The point is we are going to be connecting these unpaired electrons, these dots that are isolated in their Lewis dot structure, and in drawing these lines together, what we represent is a chemical bond, where the oxygen, let's say if we're just focusing on this oxygen and this oxygen needs 2 more electrons in order to satisfy its octet, but it's surrounded by other non-metals which also prefer to gain electrons. They all have very or relatively high electron affinities. So this oxygen, looking to the hydrogen on the left, which needs 1 more electron, says, okay, I'll cut you a deal. If you share your single unpaired electron with me, I'll share my single unpaired electron with you. In doing so, these two electrons are now being shared between these two nonmetals, and if we turn our attention over here to the kind of condensed version of the structure on the right, we can see that the oxygen, or the electron from the oxygen, and the electron from the hydrogen are now being shared directly in between. So the hydrogen has its duet fulfilled, and this oxygen has its octet fulfilled. So we're kind of splitting the difference in this compromise, where overall the oxygen, yes, would be probably maybe more stable if it just had 2 electrons on its own, but because again it's surrounded by things that don't want to give up their electrons, it's going to be more stable for the entire community if everyone just shares their electrons together. In doing so, we create a charge-neutral molecular compound. So a molecular compound is not caused by electrons completely transferring from one element to another, but rather when elements come together and kind of split the difference like this, we end up with something that is known as a molecule. All right, so molecular bonds are also known as covalent bonds. This is the result of when electrons are quote-unquote shared between 2 different nonmetals. So again, we're emphasizing there are no metals here. If metals are present, we're more than likely going to be working with an ionic compound. If we're working solely with nonmetals, we are working with a molecular compound. Now the sharing of electrons, the reason why I put this in quotes is because electrons are dynamic, aka they are always moving. The common picture for a covalent bond, let's say we're going to look at this Cl2 right here. The common picture for a covalent bond is that we have our 2 nuclear centers, chlorine on the left, chlorine on the right, and the 2 electrons that they're going to be sharing are going to be present just right in between. But this is an incorrect depiction of a covalent bond because the electrons are dynamic. Our electrons, yes, are being shared between the 2 nucleic centers, but they are not being shared statically. They're not just hanging out in between. Rather, both of these electrons are being shared between the 2 nuclei and are circling the 2 nuclei. These, if we have one electron present on the left, the other should be present on the right, but they are going to both continue fluctuating back and forth between both nucleic centers. They're going to hover back and forth between both atoms. The bond that holds these atoms together is caused by the motion of the electrons lassoing the 2 centers and keeping them together. Not only are each of the individual chlorines stabilized by sharing the electrons, but the electrons are also stabilized because they have more places to go. They can move across a greater period of, or a greater distance of space, and they are stabilized by 2 different positive centers. So long as the electrons are hovering back and forth in this way, they're going to lasso the 2 atoms together, holding them in what is known as a covalent bond. All right, the presence though of a covalent bond for this reason, because the electrons are hovering between 2 different centers, form what we know as discrete molecules. So like, for instance, if a 3rd chlorine was to come into this picture with its also 1 unpaired valence electron, would this chlorine be able to join the fray? The answer we've actually found experimentally is no. 2 chlorines coming together like this are very stable. These 2 unpaired electrons kind of hovering between the 2 atomic centers is stable. Adding a 3rd chlorine to the mix actually destabilizes the picture, and it's not likely to form a 3rd bond or a 2nd bond. We're not likely to end up with something like Cl3. Unlike ionic crystals, which can keep building so long as we have positive and negative ions, molecules can't do that. Molecules are limited by the electron configurations and how many unpaired electrons each of these species have coming together. Because molecules are discrete, we can add any number of atoms so long as we're still partnering up unpaired electrons together, but regardless of how big the molecule gets, it's still going to be just one big molecule. This goes all the way up to molecules as large as proteins. One large molecule. There we go. I was trying to spell the word molecule. Proteins are one large molecule. So if you continue in chemistry and make it up to biochemistry, or maybe you've even seen these types of illustrations before, this is a shorthand illustration for a very large molecule like a protein. If we were though to find one terminus, like one end of the protein, we'd see, like, let's say right here, there's kind of a loose thread. We can trace this thread though all the way through this dark blue, connecting to the light blue, connecting to the teal, connecting all the way over here to the green, all the way to the yellow, all the way to the orange and the red, and boom, here finally we find another loose thread. This very large, ribbony, thready kind of picture represents one very large molecule that's just folded over onto itself in multiple places in 3D space. But suffice to say, again, it's one large molecule. We have, through the combination of atoms that are nonmetals and covalent bonds, formed one discrete molecule, held together again by covalent bonds. For this reason, because molecules are discrete, our numeric subscripts in the molecular formula are not reduced to the smallest whole numbered ratios. To reiterate, because our compounds are discrete, the chemical and physical properties of something that is large, like C6H12O6, are going to be very different than the chemical properties of a molecule that is being represented with the empirical formula. C6H12O6 is table sugar, right? This is glucose. We know it's sweet to the taste, we know it's safe to touch, we use it in baking, etc. The chemical formula C6H12O6, if we were to reduce it down to the smallest whole numbered ratios, we'd end up with something that is C1H2O1. Well, this chemical formula pertains to a completely different molecule, right? It looks totally different and has completely different chemical properties as a result. CH2O is formaldehyde, which, if you've never worked with or if you've never heard of it before, this used to be, like in the olden days, used for embalming. It is a very strong preservative, but it is also highly carcinogenic. It causes cancer, right? So table sugar versus formaldehyde, these are two very different compounds. They have very different chemical and physical properties. One, though, is 6 times larger. It has 6 times the number of carbons, hydrogens, and oxygens than the other. Because of the vastly different chemical properties, we have to represent table sugar using its expanded, its explicit molecular formula. We cannot reduce the chemical formula down to CH2O because this means something totally different. All right, so ionic compounds we represent with the empirical formula because whether or not we scale up or scale down, we see the exact same chemical and physical properties. Molecules are totally different. If we try to scale up or scale down the formulas, due to the nature of how covalent bonds form discrete molecules, we're going to be observing totally different compounds, and as such, we cannot use the empirical formulas as a shortcut. All right, so because we cannot shorthand our chemical formulas, it actually makes naming our molecules very easy and straightforward because we need a systematic way that works for everything, no matter how big or how small. So we are going to learn how to name molecular formulas that are binary. This is the simplest set of rules. Binary meaning that we're going to have 2 elements inside of the chemical formula. Not 2 atoms, but 2 elements, right? 2 element types. When it comes to naming our molecules, the first element, we're just going to call it by the element name. And the second element, in much the same way as what we did with our anions before, we're going to take the element name, we're going to drop the suffix, and we're going to add IDE. This is going to, in much the same way as it did before, symbolize a chemical bond. So notice that the way that we name the second element here is not unique to the anions, right? It doesn't symbolize that we have an ionic versus a molecular bond. It just symbolizes that we have a chemical bond. There is a compound present here. The way that our molecular formulas are going to differ, though, how they are unique from the ionic formulas, is that we also have to add the following prefixes to specifically represent what the numeric subscript is in the chemical formula, right? We cannot reduce to empirical formula. And because we cannot reduce to the empirical formula, there's not going to be one kind of catch-all notation. We're going to have to be really explicit. Do you have one of your atoms? Do you have two of your atoms? Do you have three of your atoms present in that subscript? We're going to have to make sure that we include this prefix in order to tell us exactly what the subscript is. So we are following or using these, you can tell, Greek subscripts, mono representing 1, di representing 2, tri representing 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octo is 8, nona is 9, and deca is 10. And of course we would use the the following prefixes after this, like undeca would be 11 and dodeca would be 12, but we're just going to list the first 10 here. I feel like that's enough. So for example, if we want to start putting each of these together, I'm just going to clean up the slide really quick. Boom. So let's say we want to name something like N2O, right? This is a binary compound. We have two different elements here. We have nitrogen and oxygen. So let's just go through the process and name this molecule. And again, we know it's a molecule because both of these elements are non-metals. So regardless as how the compound is going to look, of which in chapter 6 is when we're going to finally learn how to draw these things for ourselves. So we're just putting a pin in how it looks. We can still name the compound based off of the formula present here because we know how many of each element need to be present. All right, so nitrogen. Our first rule says that the first element in the formula just gets its element name, nitrogen. And our second element in the formula is going to have its name. We are going to drop the suffix and add IDE. So we've already seen something like oxygen. We drop the suffix of the igen. We add IDE. This gives us oxide. All right, so far we have the name nitrogen oxide. In order to specify exactly how many nitrogens and how many oxygens, we're going to use our Greek prefixes. There are 2 nitrogens, so we're going to add a di in front of the nitrogen. And there is only 1 oxygen, so we're going to add a mono in front of the oxygen. Now, mono-oxygen looks a little strange, so we're actually just going to remove one of these O's. It's going to be monoxide. So our total name ends up being dinitrogen monoxide. And that's how we name our molecular formulas, right? The process is really straightforward. So long as you know what your chemical formula is, you know which prefixes to use, and so long as you can identify the element names, you already know what to call the elements, and you know how to shorten the second element name by dropping the suffix and adding IDE, because we've talked about this already. The only kind of caveat, the only exception to these rules is if your first element only has one of that thing present inside of your chemical formula. So let's say NO2, right? So we're just gonna, instead of having 2 nitrogens and 1 oxygen, we now have 1 nitrogen and 2 oxygens. Well, if we follow the same naming convention, the nitrogen comes first, oxide comes second. If the element that is listed first, you only have 1 of, you drop the prefix. It's just a shorthand way to, or like a way, I guess, to condense the naming formula. So we don't have to add the prefix of the mono here. It's just nitrogen. And the reason why I suspect we do this is because there are so many molecules where the first element that's listed, there's only one of. To have to keep writing mono over and over and over again for all of these chemicals, for all of these names, it would just be sort of redundant. I mean, if you're listing an element, you have at least one of it. And because the second element that's listed, oftentimes there's more than one. If there is just one, like in our first example, the dinitrogen monoxide, we had to list the mon because it's very rare for the second element to only have one of it present. All right, so this is our only exception. If your first element, there's only one of it, you drop the mono. Otherwise, if it's on the second element or the third element, the fourth element, you will include the mono. Our oxygen, just to round this whole example out, there are two of them. So we are going to write a di here. Nitrogen dioxide is the name for this chemical formula. Okay, now we've seen a couple of examples on how to partner, write the first element, the second element, and the prefixes. So I'm just gonna give you guys some time to work through some similar problems. So either what is the formula or name of the following molecules? All right, so let's just come back together and go through each of these one by one. So PBr5. We're going to, since it's a chemical formula, go through our naming convention. First is phosphorus, phosphorus, and second is bromine. Since this is the second element that is being listed, we're going to drop the suffix of the INE, and we're going to add the IDE. So far we have phosphorus bromide. Now we can see we only have one phosphorus present at the beginning, which means we drop the mono. There's nothing extra that we need to add in front of the phosphorus. Our bromide, there are 5 of them. So we're going to add the prefix of penta in front of the bromide. Phosphorus pentabromide. 1 phosphorus, 5 bromines, 1 molecular compound. All right, sulfur hexafluoride. We can see again an example of there is only 1 sulfur, and we can assume this because there's nothing present out in front. There's no, like, not even a mono that is listed. So our sulfur, there's only 1 of it. I'm just gonna write it over here for more space. Sulfur. Hexafluoride, hexa meaning that we have 6 of our fluorines, fluorine with a subscript of 6. And that is our chemical formula for sulfur hexafluoride. All right, FCl. We're going to write out the elemental name that is listed first, fluorine, and chlorine comes second. And since it comes second, we're gonna drop the suffix and add IDE, so we're looking at fluorine chloride. Now to specify that we only have 1 of these chlorines, we're going to add a mono in front of it. And because fluorine is the first element, we drop the mono. So our total name here is fluorine monochloride. All right, second from the end, dihydrogen monoxide. Our first name tells us that we have 2 hydrogens, and our second name tells us that we have 1 oxygen. Well, would you look at that? Dihydrogen monoxide is the fancy scientific name for water. So if you really want to wow your friends and family over midterms, Thanksgiving, Christmas, just tell them that you learned this neat fact. Dihydrogen monoxide is the proper scientific name for water. All right, and last but not least, nitrogen dioxide. We have 1 nitrogen present. Dioxide meaning that we have 2 of our oxygens. And here we can see that we've gone in the reverse of the previous example that we've just listed, right? So on the previous slide, if we go backwards, we started with NO2 and we named it nitrogen dioxide. And now moving forward, I gave you guys sneakily the name of nitrogen dioxide, and here you wrote the formula. So if we know the prefixes, if we're explicitly given the prefixes, again, we know exactly how many of each element need to be present inside of this chemical formula. It's actually a much more straightforward way for writing and naming things as opposed to the ionic method. All right, but we're not stopping there. We have a couple of additional molecular compounds that we need to introduce and talk about their naming conventions. These are specific subsets of the molecular description. First and foremost, we're going to talk about polyatomic ions. This name literally translates to many atoms, right? Polyatomic with a charge, ion. I do not ask or expect for much memorization inside of my class. And if you're just casually coming across these videos, obviously you can do whatever you want to do. But if you are actually in my class, then these polyatomic ions are going to have to be something that you have to know. The reason why you're going to have to know these polyatomic ions is because, especially the ones present on this table, this is not an exhaustive list, but the ones that are on this table are the most common, and we will see them all the time. In fact, we've already been working with compounds that contain these ions in lab, in other examples. So it's going to be really important to recognize that if you're working, let's say, with a chemical that is comprised of a nitrogen, a hydrogen, or 4 hydrogens and something else, let's say NH4 Br, you're not going to try and name this using our previously defined convention. This is not nitrogen hydrogen monobromide. That is not the name of this thing, because NH4 is a really common pattern that we see in bonding, because these elements come together so many times and form this polyatomic ion. The name for the compound that is listed here is actually ammonium bromide. Right, we have to be able to recognize this pattern, NH4, as it appears in certain compounds, because NH4 has a very special name. And that is true of any of the polyatomic ions on this list. If you see CO3 in a compound, or OH in a compound, or NO2 with a minus charge inside of a compound, each of these things have very special and specific names. So you're gonna have to be able to recognize these. And this entire table, you can either pause to kind of copy down the polyatomic ions, or if you are, again, actually in my class using the 4th edition of Burge and Overby's Chemistry Atoms First, this can be found as table 5.10 in the text. All right, so when it comes to writing formulas or writing out the names for these species, we are going to treat polyatomic ions like any other defined element. So we are going to assume that they have a special block on the periodic table because they come as a unit. We must determine the stable charges on our cations and anions if not given. So notice that we are following in the first rule and the second rule. We are treating these polyatomic ions as ions and following the ionic conventions. So we need to know the stable charges, and we need to know how many of the cations and anions we need to make a charge-neutral compound. All right, so let's write the chemical formula for the combination of magnesium with a 2+ charge and the polyatomic ion known as hydroxide. This is OH with a minus charge. Now we are going to want to keep the OH with a minus charge together. Again, we're going to treat this like any other predefined element. It just has its own special name. It comes as a pair. So because it comes as a pair, we're going to keep it together. Magnesium comes first. We can see that the magnesium with a 2+ charge is going to need 2 separate OH minuses to cancel out this positive 2 charge, right? Because if we only have one OH minus, this is going to leave a +1 left over. So we're going to need 2 of our hydroxides. Now notice in the chemical formula as I have it written, doesn't explicitly say that we have 2 hydroxides. As we have learned, our previous convention states that our subscript follows immediately after the element of which there is that many of. So we actually need a special notation, a special addition to our chemical formula to also show that we don't just have 2 hydrogens, we have 2 oxygens as well, right? Hydroxide comes as a unit. In order to signify this, we add parentheses. And much like math, if there is a subscript present outside of parentheses in chemistry, we distribute that subscript to everything that is inside of the parentheses. So if we're working with an ionic compound that is a combination of 2 magnesium, or that is a combination of magnesium with a 2+ charge and 2 hydroxides, we're going to need 1 magnesium and 2 of the hydroxides. So we're going to put parentheses around the hydroxide and scale up the hydroxide as a whole unit by 2. All right, so our total formula ends up looking like Mg parenthesis OH parenthesis subscript of 2. If we wish to name a compound that contains some type of polyatomic ion, all previous rules for main-bodied elements and transition metals apply. If, again, we are following ionic conventions. So we may be working, like when we're working with polyatomic ions, we may be working with a molecular compound that has a charge, but because it has a charge and there's going to be some type of counter ion present, we need to turn our attention instead to working with the ionic conventions to really make sure we have a proper charge neutral formula and a proper name to go along with it. When naming our species though, when naming our formula, if there is a polyatomic ion present, we do not change the name of the polyatomic ion. So we are not going to drop any suffixes of the polyatomic ion. We're not going to be adding IDE to the polyatomic ion. The polyatomic ion name is special and we will not touch it. Otherwise, we might start confusing the identity of a polyatomic ion for something else. So let's observe these 2 chemical formula and name them using the previous ionic conventions. If we are working with something that looks like, and we can see there's some parentheses here, NH4 with a subscript of a 2, capital S, well, parentheses are a huge red flag. Parentheses signify polyatomic ions. So even if you're still working with, like, you haven't quite memorized the table yet, you kind of have it sitting next to you, anytime you observe a chemical formula that has parentheses, you are working with a polyatomic ion, and it's safe to kind of look through that table and see if you can't find the polyatomic ion in the table. All right, so our polyatomic ion here, just to go back to our table, we can observe, cleaning this up, NH4 with parentheses around it signifies that we are working with something that has a +1 charge, and its name is ammonium. So the name that's going to be listed first, right, we're just naming this element, quote unquote element, is ammonium. And the S that comes afterwards, since this is a main-bodied ion, we are going to just name it straight up by writing out its name, dropping the suffix, adding the IDE. So sulfur becomes sulfide. Because we are working with ionic compounds, notice that we do not have any Greek prefixes here. We do not need any Greek prefixes. Since the compounds need to be charged balanced, each of these NH4s is going to have a plus charge. There are 2 of them present, meaning a +2 charge overall. Our sulfur naturally has a 2- charge, and so the whole thing's going to be charged neutral. The ammonium, we are just going to write out as ammonium. The sulfide, we will write out as sulfide. All right, and turning our attention to the Cu2, SO4. There are no parentheses here. However, we can see that we have one metal and multiple nonmetals. If our chemical formula is set up with this type of pattern, metal plus nonmetal plus nonmetal, this is also a huge red flag that you are working with a polyatomic ion, because we're either, like in the rules that we've learned previously, we've only ever learned metal and nonmetal, or nonmetal with nonmetal, right? If there's a metal and a nonmetal, this is ionic. If it's nonmetal, nonmetal, this is molecular. So what does it mean if you have all three of them put together? It means that something is going to be a polyatomic ion here. And if we turn our attention to the formula, we can see that there is a copper, a sulfur, and two coppers, sorry, a sulfur, and 4 oxygens. Let's go see if we can't find a polyatomic ion that has this pattern, SO4. Well, if we look through our table, aha, here. There is an SO4 with a 2- charge present, and this thing is known as sulfate. So if we turn our attention then back to this chemical formula, it would appear as though this nonmetal is not going to have to be named individually, because SO4 means sulfate. And we don't have to drop the suffix here, we don't have to add an IDE, because the polyatomic ion of SO4 has a special name. We keep the entirety of the special name. Now, copper is going to go in front of this. Since copper is not a part of a polyatomic ion, we're going to write it out in front, because this is then, in combination, an ionic compound. There are not going to be any prefixes, but there is something missing. Our copper is not just a metal, it is a transition metal. And since it's a transition metal, we're going to need to present what its charge is in parentheses here in order to be explicitly clear about, like, of all of the options that copper can have, what is the charge of our copper in this specific compound? Well, since each of the, because there are 2 different coppers here, they're going to need to balance out the charge on the sulfate. Our sulfate has a -2 charge, and this we know, just going back to the table, there's a 2- charge on our sulfate here, so we are going to need to have a total number of coppers to balance out this -2 charge. Well, since there are 2 coppers, it's pretty safe to assume that whatever the charge of the copper is going to be divided between both of them. And because the sum of our coppers are going to need to balance out this -2 charge, the sum should have a +2 charge. Well, if we take 2 and divide it by 2, this means that each of the individual coppers is going to have a +1 charge, and inside of the parentheses here, we're going to have a Roman numeral 1. So the total name for this compound that contains a polyatomic ion is going to be copper 1 sulfate. This only leaves one additional special case left. So far today we have talked about, just a quick review, molecules, how they are held together by covalent bonds between non-metallic atoms, how we name those molecular units because they come in discrete molecules, right? We can't just add any number of elements together. A very particular molecule has a very particular chemical formula, and therefore will also have a very particular name. Building off of that, though, what happens if we have multiple elements, multiple non-metals together forming a molecule with a charge? We get polyatomic ions, which is what we've just talked about. And there is one special case left: acids. So acids are molecules, specifically, which have been found to donate H+ to solution. So how do we know at this level when something is going to donate H+ to solution? In the chemical formula, we're going to have an H listed out in front. If H is listed in front, it is safe to assume that we are working with an acid. And if we're working with an acid, we're going to have to follow some very special naming conventions because acids have a very special property to them. Not everything can donate H+ to solution. And in affecting the pH balance, it turns out that these molecules are pretty pivotal for things such as forming life on the planet. So we give them a special naming convention to reflect that. Now, to name acids, we are first going to follow the ionic naming conventions. This is going to give us a really nice setup. So let's say hypothetically we are working with H2S, which we can see illustrated down below. We have a single sulfur and 2 little hydrogens kind of bound off of it. The name that we would give to this compound following the ionic naming conventions is hydrogen sulfide. So that's good, that's well and good, hydrogen sulfide. How we make this name special, following this new rule for the acids, is if your acid name ends with an IDE, which it should if we're following the ionic naming convention, we are going to shorten the hydrogen to hydro, and the second element listed that ends in IDE, we are going to change that IDE to ic acid. So hydrogen sulfide, we're going to drop the second part of hydrogen, we're just going to leave it at hydro, according to this rule. And the sulfide, we are going to drop the IDE and add ic acid. So we can either write sulfic acid, or the more like kind of common way to say it, just colloquially, is sulfuric acid. So hydrogen sulfide becomes hydrosulfuric acid. This special name, again with acid explicitly present, tells us the chemical formula and the picture for what our molecule is going to look like as it interacts like with water. And this is going to become more important as we start approaching chapter 9, but it's still really nice to kind of lay out this convention early while we're talking about naming things. All right, so there are also, though, some very special forms of acid that are out there. And we call these Oxo Acids. So how these special acids differ from our previous sort of like generic acids, they are known as Oxo Acids, and this is meant to reflect the fact that they contain one or more oxygen atom as well as the hydrogen and the additional element. So the Oxo Acids are going to contain some type of polyatomic anion. So this, the Oxo Acid example is tying together our molecules, polyatomic ions, and acids into one big final example. And as an example, let's pay attention to this molecule right here, which has a sulfur in the middle, 4 oxygens off of that sulfur, and 2 hydrogens off of 2 of these oxygens. When we put this together, we get H2SO4. Now we are going to, in much the same way as the previous acid, name this compound using the ionic rules before we address these 2 rules listed here. So we're going to follow the ionic rules. Our element that's listed first, we just call it what it is, hydrogen. And because a polyatomic ion is listed second, we are going to name the polyatomic ion without altering its name at all. This will become sulfate. So far, we are working with hydrogen sulfate. And here is the moment where we turn to our special rules off to the side. These 2 rules are mutually exclusive. We're only going to follow one or the other. So if your molecule, if your acid so far, contains an oxo anion ending in ATE, which ours does, sulfate does end in ATE, we're going to drop the hydrogen completely. So we're just going to drop this and change the ATE to ic acid. So this could be known as sulfic acid, or more colloquially, it is known as sulfuric acid. Now, if hypothetically our oxo anion had ended in ITE, we would drop the hydrogen, change the ITE to Oxo acid. So there are a couple of examples of polyatomic ions that end in ITE. If we go back to the table, all the way back to the table and clean this up, we can see, for instance, right here, there is a polyatomic ion that ends in ITE. What this means is if we were to partner this with a hydrogen, H out in front, because they naturally kind of have plus charges, ClO2 with a single minus charge, everything's charge neutral here, we would call this at first hydrogen chloride. And following our special oxo anion, oxo acid kind of rule, we would drop the hydrogen and change the ite to Oxo acid. So HClO2 could potentially be called hydrogen chloride. That's a perfectly valid name. But if we want to acknowledge what a special molecule this is, we're going to follow our secondary naming convention and call it Oxo acid instead. All right. So with that, now that we have covered naming molecules, things that contain polyatomic ions, and things that have acidic properties to them, we're going to call it a day. So here we have some example problems for covalent bonding present in molecules. So this is how we describe covalent bonds. Naming molecular compounds. So how do we actually name the things with those prefixes, the Greek prefixes? And covalent bonding in ionic species. This all has to do with polyatomic ions and acids. So if you want to get a little bit of practice on the species that kind of have some ionic behavior but also covalent behavior, we have some example problems for that as well. All right, so double check to see if you have homework to do, and until next time, class is dismissed.